This section of our unit on chemical reactions is kind of a broad range of dealing with chemical reactions. Today is kind of a primer to chemical reactions. And some of this will be review for you, so that's good. That'll make the beginning of this section of our unit a little easier. So in chemical reactions, something you need to keep in mind is that mass, energy, and then the new thing you might not know about, and charge are all conserved. You may have actually learned in the past in your science classes the law of conservation of mass. The law of conservation of mass states that the mass of the atoms at the beginning of the reaction must equal the mass of the atoms after the reaction. Real simple concept that you cannot create or destroy any mass in a reaction. It can sort of change forms. It can change from one compound to a different compound, but you can't create or destroy mass. All of the masses on the reactant side, that's the beginning of the reaction, must equal the total masses on the product side of that reaction as well. So let's write that out. Mass of atoms before the reaction, and I'm going to abbreviate reaction RXN. That's a really common abbreviation that chemists use. So the mass of the atoms before the reaction must equal the mass after. And we're going to start dealing with that in this section of the unit when we begin balancing reactions. You can't create or destroy atoms. They can form different bonds, but you can't create or destroy atoms. The other thing we're going to talk about in this unit is that energy piece from up above. We're also going to discuss energy and how it cannot be created or destroyed. The third part of that, this charge part, it's true, it cannot be created or destroyed. It must be conserved in a reaction. We're not going to address that in this unit, but I wanted to bring it up now because very often on your Regents exam, you're going to see a question that asks what must be conserved in a reaction. And you get the choice mass only, mass and energy only, mass, energy, and charge. And it's all three always are conserved, although we won't discuss charge until we get into oxidation and reduction. All right, some things you may have learned before about energy changes in a reaction. There are exothermic reactions and endothermic reactions. Exo actually comes from the Latin exao, those of you that are Latin scholars. Therm, I believe that's actually Greek. It means heat. So exao, it actually means the same thing as exit. So this is when heat leaves a reaction. So we're going to lose heat. Now, let's imagine we have this reaction happening in this little space here. If it's losing heat, heat is exiting that reaction. If you were to touch that with your hand, how would that feel? That would actually feel warm because you can feel the heat coming off of it. So an exothermic reaction feels warm to the touch because it's losing heat. I'm going to say hot because you want to be careful when you're touching things. It might actually be really hot. So an example of something you may have experienced before that's an exothermic reaction. You ever buy hot hands? Maybe to go to a Bills game or something like that to keep your hands warm. When you activate that, you're actually starting a reaction that is exothermic, and that's why it feels warm against your hand. So you may understand then that the next one, endothermic reactions, they actually absorb heat. Endo means inside, into. So the heat is being pulled inside. So again, looking at my silly little drawing over here, if I have my reaction occurring here and it's drawing heat into the reaction, if you hold your hand up and touch that, it's actually going to draw the heat out of your hand. And when it does that, it's going to feel cold. That's kind of counterintuitive, but that's the way it works. So this is actually going to feel cold. It's going to draw the heat out of your hand because it wants that heat in order to make the reaction occur. An example of that, in the same line as those heat packs, the hot hands, they have ice packs in first aid kits. You snap it and it starts a reaction and it feels really cold because it's going to be absorbing heat from the environment and feel cold as a result. Some other terms that you've probably learned before: potential energy. Potential energy is stored energy. All right, we're going to talk quite a bit about potential energy and how that changes in the course of an exothermic and an endothermic reaction. I also like to think of potential energy as the energy of position. So I'm sure when you've talked about potential energy versus kinetic energy, you've looked at an example of a ball rolling down a hill. When it's sitting at the top of the hill, it has a lot of potential energy because of its position at the top of the hill. Once it gets to the bottom of that hill, it doesn't have nearly as much potential energy because it's as low as it can be. Gravity isn't going to pull it down any further than it is. And then, of course, kinetic energy. Kinetic energy is the energy of motion. This is going to come up throughout the year. So this is a measure of how much the particles are moving. And we're going to talk about average kinetic energy being temperature. Average kinetic energy and temperature are interchangeable words. All right, to continue our primer of chemical equations, you're going to often see some compounds written on this side and some compounds written on this side, and they're separated by what we call a reaction arrow. The compounds that are on the left side we call the reactants, and the compounds we see on the right side we call the products. So if we had an endothermic reaction, since it needs heat, it's going to draw in heat in order for the reaction to occur. Heat is actually going to be a reactant in our equation. It needs that heat in order to have the reaction actually occur. It's going to be one of the reactants, and therefore when we write heat or energy into an endothermic reaction, it's going to be on the left side, or the reactant side of the arrow. So I'm going to write out a generic form of a reaction so you can see how heat would be written in. We might have compound A and compound B and heat. Now we measure heat, so I'm just picking 22 as a number, in kilojoules. So the heat is on the left side, then our reactant arrow, and then our product or products depending on the reaction. With an exothermic reaction, heat is going to be leaving, heat exiting the reaction, so the heat or the energy will be written on the right side or the product side of the reaction. That's why it can leave and you can feel that heat on your hand. So this would look similar, except that you would have A plus B, then the reactant arrow, then your product, and whatever heat value you may have. So speaking of those heat values, we measure heat in kilojoules in chemistry, and we're going to actually use something you've seen before in math class, probably, that Greek capital letter delta. And delta, whenever you see it in math or in science, it means change. And H is meaning heat. So the change in heat. We call the change in heat the heat of reaction. That's our term for delta H, heat of reaction. And it measures essentially the changes in the potential energy that occur during a reaction. If delta H is positive, that means it's absorbing heat. In the end, you're going to have more heat absorbed or more potential energy absorbed in that reaction. So that's why delta H is positive. So whenever delta H is positive, you have an endothermic reaction. Whenever you have delta H being negative, you have an exothermic reaction. In an endothermic reaction, the potential energy is increasing. In an exothermic reaction, the potential energy is decreasing. We're going to talk more about this on the back side, but you have a table labeled Table I in your reference tables that lists the heat of reaction at 101.3 kilopascals. That's standard pressure. So on a normal day, the pressure is 101.3 kilopascals and 298 Kelvin. 298 Kelvin is about room temperature. This is different than most of the other tables you're going to see in your reference tables. Most of the other tables are based on standard pressure, but they're based on what we call standard temperature, which would be 273 Kelvin or 0 Celsius. Standard temperature is 0 Celsius. This is essentially 25 degrees Celsius, which is about room temperature. This is the only table that I can think of in our reference tables that references room temperature. So if you ever see a question that references standard pressure, but it's not standard temperature, they're probably referring to Table I, and they love to leave out that they're referring to Table I just to trip you up. But if you see these two values, you know you've got Table I. Anyway, this is a list of a bunch of different reactions and the corresponding change in the heat or the change in the potential energy in each of these reactions. Note that some are negative, and there are a few in here that are also positive. If you ever forget that when you have a positive delta H, that it's going to be endothermic, and a negative delta H means that it'll be exothermic, you'll actually see this little sentence down here. It says a minus sign indicates an exothermic reaction. So you have a little reminder there if you ever need it. So now we're going to use Table I and apply it to some chemical reactions. This first reaction we're given, we have our reactants on the left side of the reaction arrow and our products on the right side. And one thing I noticed right away is they've given us a value of kilojoules in our equation. So we're already given our change in potential energy or our delta H value. What they haven't told you is what the sign of delta H is, if it's plus or if it's minus. You can't tell that from the number the way it's written in the reaction. What you can tell is the sign based on which side of the reaction arrow it is. So here's our reaction arrow. On the front side of our notes, we said that if heat is on the right, which this one is, it's going to be exothermic. And we indicate that it's exothermic by giving a negative sign and then the value. Okay. Another way to remember this, up above I've put that plus and that minus. My reaction arrow goes in between like so, and now I know if it's a positive delta H, it goes on the reactant side, just like the plus is here. If it's a negative delta H, it goes on the product side or on the right side. But you never write it in as a negative value. The negative is only telling you which side of the reaction arrow to write it on. you don't put a negative value in an equation. That'd be like saying, oh, I got some bacon and eggs and Bisquick, and I made bacon minus pancakes. We don't make minus pancakes. We made bacon and pancakes, okay? These are all essentially recipes for making different things. So you never have a minus in a recipe. All right, the rest of the columns that we have to fill in is this endo or exothermic. This is exothermic because our delta H value is negative, or you could have recognized that based on the fact that the heat was written on the product side or the right side of the reaction arrow. The potential energy change, since our delta H value is negative, and delta H is essentially the change in the potential energy, our potential energy went down. Our kinetic energy, however, must have gone up in response because our total energy change is always zero. Remember, we can't create or destroy energy. It can change forms. In this case, it changed from potential to kinetic energy. Those molecules are now moving faster because they're warmer. Next equation, we're given our reactants and our products. There's no heat written into this equation. So we need to use table I to find our heat. And sometimes this is tricky because there's some equations that look very similar. So you want to make sure you're checking your phase of matter and these numbers in front of the compounds, which we call coefficients. So let's see if we can find one just like this. Close. There's no coefficient in front of oxygen, and there's no subscript of 2 on that nitrogen. Here it is right here, and it's positive 66.4. Which means, since it's positive, it's endothermic. Delta H is essentially equivalent to potential energy, so the potential energy went up. Therefore, the kinetic must have gone down, and our total energy change is always zero. Let's try another one together. We have 2C solid, 3H2 gas, and C2H6 gas created. I think that's right here, yep. And our delta H is negative 84.0, which makes this exothermic. So the potential energy must have gone down, therefore the kinetic went up, and our total energy change is always zero. Next one, we're actually given our heat in the equation. It is on the reactant side, which means that it's positive, right? You can always reference up here if it's positive on the reactant side. 227.4, endothermic, which means potential energy went up, kinetic went down, overall change is zero. I'm going to do one more with you, and then you're going to do the rest on your own. This next one, we have KNO3 solid becoming K plus AQ means aqueous, meaning it's dissolved in water, NO3 minus aqueous. So really what's happening in this equation is they've taken a solid and they put it in water and it dissociated into ions. This may help you to find different equations because the ones that do that are kind of all lumped together at the bottom of the table here. All the rest of these are true chemical reactions, where these are reactions of dissolving. Not all reactions, when they dissolve, either produce or absorb heat, but there are a few, and they're listed here. This is this one here, and it's a positive 34.89 for the delta H, which means it's endothermic because it's positive. Potential energy and delta H go hand in hand, so this is going up, therefore this must go down. because the total energy change in the system always has to be 0. Go ahead and try the last 5. You may be asked to answer some of your answers into Edpuzzle, and the rest you can check when you're done. I hope this was a good primer for you as we begin exploring chemical reactions.